Hello, everybody. My name is Lily Shu, and I'm a PhD student at Harvard. Thank you for coming to my poster, even though we can't all be in Dallas together, unfortunately. I'm going to be presenting our paper called Stay Ahead of Poachers, Illegal Wildlife Poaching Prediction and Patrol Planning Under Uncertainty with Field Test Evaluations. This is joint work with other researchers at Harvard, the University of Southern California, Key Biodiversity Area Secretariat, the Worldwide Fund for Nature, the Wildlife Conservation Society, and the Uganda Wildlife Authority. Our motivating domain is poaching. Poaching is the legal hunt or capture of wild animals, and it threatens animal populations, biodiversity, and ecotourism. It's motivated by the illegal wildlife trade for goods such as ivory, animal skins, bushmeat, and traditional medicine. The primary method of combating poaching is through ranger-conducted patrols. Here, we're working specifically with rangers from the Uganda Wildlife Authority and WWF. Rangers will go on national parks and conduct patrols where they search for snares which have been set out to ensnare animals. And they also will look for other signs of illegal activity, such as trespassing, as shown here by ashes from a legal campsite. The rangers will conduct the patrols with the GPSs and make note of all the observations, which get uploaded to a database called SMART. And then over time, SMART records a wide variety of all the historical patrol observations made over the years. However, this data is imperfect. Like many real-world data sets, it suffers from extreme class imbalance, in which the positive instances where we actually found illegal activity are quite scarce compared to the negative instances where rangers patrolled an area and didn't find anything. So the imbalance would go up to about 1 to 200 in this case. And there's also extreme uncertainty in that when we found illegal activity, we know for sure that's a positive label that because we saw it. But for the negative labels, just because we patrolled somewhere and didn't find anything doesn't mean that there wasn't actually poaching activity there. It could be just we didn't patrol sufficiently in that area, or we just missed looking for it underneath some dense grass, for example. So we cannot be completely certain about the negative labels in our set. So in this work, we offer two contributions. The first is to incorporate Gaussian processes to quantify predictive uncertainty and improve the robustness of our prescribed patrols using that uncertainty. And we also conduct large-scale field tests in Uganda and Cambodia to show that, that our methods perform well on the ground as well as in our lab experiments. To begin, we'll delve into the wildlife crime domain. So we're working specifically with two parks in Uganda, as mentioned, Queen Elizabeth National Park and Murchison Falls, and also a park in Cambodia, Srepok Wildlife Sanctuary. To just look a little bit into what's at stake, Srepok Wildlife Sanctuary is on the border with Vietnam, and it's home to a wide variety of animals, most notably the Asian elephant. So in Srepok Wildlife Sanctuary, we have over 40,000 patrol observations recorded over a 5-year time period. And to process this data, we'll discretize the historical patrol effort into 1 by 1 kilometer regions. And then we'll also record all of the instances of illegal activity observed in the data set. So this includes weapons such as firearms and traditional weapons, traps and snares, animal carcasses, and even poachers confronted directly. So all of that becomes our illegal activity. And then this gets built into what we call the Protection Assistant for Wildlife Security, or PAWS, as we affectionately like to name the system. The PAWS takes as input data the illegal activity and patrol effort shown on the previous slide, and then also geospatial information about the land, including roads, rivers, and land cover, which we discretize. From this input data, we'll use machine learning to generate predictive risk maps that indicate hotspots for poaching. So we have risk maps for both overall risk, dry season, and rainy season. And with those predictions, we use optimization to generate patrol routes, trying to figure out where best to allocate our scarce range of resources. So in this paper, we're specifically offering two things to this pipeline. The first is to incorporate Gaussian processes as our predictive learning tool to quantify uncertainty. And then we use that uncertainty in our patrol planning optimization. So the first stage of predictive modeling, again, is dealing with the issue of class imbalance, which actually differs between our data sets and is not as much of an issue in Murchison Falls, but is a significant issue in Srepok Wildlife Sanctuary. We're using an ensemble technique called I-where-E in order to address this imbalance. And I-where-E was introduced with two options for weak learners. First was bagging SVMs, and the second was bagging decision trees. However, what we offer are GPs used instead for the ensemble. And previously, decision trees had the best performance, but what we show is that Gaussian processes meet the performance of decision trees. So by adding uncertainty, we're not losing predictive performance. And in fact, on data sets that have extreme class imbalance, such as Srepok Wildlife Sanctuary, where we look only at the dry season, in these instances with even more stark data imbalance, we show that Gaussian processes actually exceed the performance of decision trees by a significant amount. So in this data set, for example, there are over 30,000 patrol observations, only 0.25% of which are positive. So the output that we get from our predictive model are poaching prediction hit rate, which is the likelihood that we'll find illegal activity if we patrol a certain area, and then also uncertainty. So with these two aspects of our predictions, we can now move on to the patrol planning stage. So the patrol planning problem is addressed with a mixed integer program to optimize for the patrol route that will maximize the likelihood of us finding illegal activity across our patrol, subject to a budgetary constraint in which we can only patrol a certain distance, and also path constraints in that we have to follow a contiguous path, and that we have to start and stop at a patrol post in the park. So what we're doing is we're taking the objective of this problem and modifying it with uncertainty. So traditionally, the utility of patrolling a cell is just given by the predicted likelihood that we'll detect illegal activity there. What we're adding is a risk parameter. So we integrate the uncertainty of our predictive models along with a scaling term beta, which allows us to control our uncertainty. So larger values of beta, which are positive, suggest a pessimistic approach where we are risk averse and patrol less in cells with greater uncertainty. We can also set beta to be negative, in which we are risk seeking and trying to explore more in areas where we do have that uncertainty. And through our simulations, we show that by taking a risk averse approach, we are able to significantly improve our ability to detect snares. Finally, we'll move on to the real-world deployment of this work, in which we conducted field tests in Uganda and Cambodia. So the structure of our field tests, I'll talk specifically about the ones in Cambodia, which we started in December 2018. We generated predictive maps of poaching likelihood in this park based off the methods discussed previously, and then identified areas that were predicted to be high risk, medium risk, and low risk according to our model. Then we picked 5 of each of those, so sent park rangers to 15 total areas throughout the park, 5 of which were high risk, 5 of which were medium risk, and 5 of which were low risk. And to ensure that this was a fair blind experiment, we did not tell park rangers which areas were of which category. So park rangers spent a month patrolling the areas that we sent them to. Pictured here is a team of park rangers from Srepok Wildlife Sanctuary with the findings from a single patrol. including hundreds of wire snares and 3 chainsaws confiscated from illegal loggers. And I just want to take this moment to give a big thank you to all of the park rangers in Srepok and elsewhere around the globe who are there on the ground to make this all possible and are actually the ones putting their lives on the line to save animals. So the results of our field test experiments in Cambodia are as follows. We found, again, we sent them to 15 areas, which were high, medium, and low risk. And given the patrol observations that they returned to us, they found significantly more illegal activity in the high risk areas than the medium risk areas, and actually found no instances of illegal activity in the low risk areas. And all of this is despite the rangers exerting a similar amount of effort across the different target groups. So this really suggests that by using this method, we would be able to suggest more efficient and effective patrol strategies for rangers, because currently they're unequally spending their time on areas that might not be very fruitful for poaching detection. To add a bit more concreteness to all of this, in that first month of patrols, rangers confiscated over 1,000 snares, 42 chainsaws, 24 motorbikes, and even a truck from poachers. Additionally, we had conducted tests previously in Uganda that showed similar results, in that the predictive model is able to effectively discriminate between poaching risk groups. Additionally, because we here are very focused on the application of our work, we believe that it's very important to see your data. So in February 2019, we spent a week in Cambodia meeting with WWF employees and going on the ground in Srepok Wildlife Sanctuary, where we camped out with park rangers at their patrol post and even got to accompany them on a motorbike patrol. To bring this all together, I just want to discuss a few lessons learned from deployment. So one of them is the challenge of variation over time. The situation on the ground changes drastically. So in Cambodia, for example, they had a significant increase in logging activity in the nearby park, so rangers had to be diverted to helping out in that park instead of being in Srepok. So previous work in this area analyzed the effectiveness of their strategies by comparing it to what rangers had found a year previously, but that's not a very good test because things will change on the ground drastically. So field tests must be self-contained, which is why we chose different predictive risk groups and made that a blind experiment. We also integrated insight from domain experts, such as seasonality. So through discussions with the people on the ground in Cambodia, we learned that there are significant differences in poaching behavior between rainy season and dry season. So we produced separate maps for those. And lastly is just thinking about the importance of ensuring effective technology transfer. So in order to take artificial intelligence technology and make it useful for wildlife conservation, we had to have regular monthly Skype calls with our collaborators. We conducted a field visit where we visited them on the ground, and we also worked with them to deploy field tests on the ground. Finally, I'd like to point out that the database system that I mentioned earlier, SMART, which is used by rangers to track their observations, is the standard system used by parks all over the world, over 800 parks in over 60 countries. And we are currently working with SMART to integrate the PAWS pipeline into their system. So we will be able to democratize AI and make our poaching predictive components available to park managers all around the world. Thank you very much. I'm happy to chat more in the sessions, or feel free to send me an email. I'd love to talk more. Thank you very much for listening to my presentation.